Very good. Well, thank you very much. Good morning. I hope everyone had a good time. I actually escaped early so I could get some sleep. Sarah, feel free with my 10 minutes or 5 minutes to my 10 minutes. Just tell me. So, again, thank you. Amazing work, an amazing opportunity to think about prevention. So let me start by saying the way I think about problems and solutions, I'm trained to study problems. I spent much of my early career studying phthalates, flame retardants, BPA, and realized we didn't make much progress in driving solutions. So I look at this from the perspective of a basic researcher who's done studies on problems, but I've also directed a center at UMass Lowell called the Toxics Use Reduction Institute, which works with industry to drive and adopt better chemistry. I created and lead a group called the Green Chemistry and Commerce Council, which works with companies across the value chain from large chemical majors to innovative startups to brands to retailers, all along the value chain to drive solutions at scale. And then we created a professional society for the field of alternatives assessment called the A4, and several members of the A4 in the room, to really bring together the interdisciplinary science of problems combined with the science of solutions to drive those changes more effectively. So top line messages for today that I want to just focus on is it's going to be difficult to have safe and sustainable chemicals or to get rid of the bad unless we have a supply of the good. We need a supply of the good, and we often don't focus enough attention on the good. How do we drive that better? Alternatives assessment is pretty key for that process of both understanding the trade-offs and evaluating, identifying, evaluating, and adopting those solutions, but also identifying where we need more research and innovation to drive solutions because there aren't better or they're suboptimal solutions. But understanding that that's not enough. Just identifying alternatives doesn't get them into the marketplace and into scale. Substitution is difficult. And then lastly, we need to break down our silos between chemists, engineers, and health scientists, ecologists, scientists, policy analysis, because in the end, it's going to take an ecosystem of science to make the change happen. So this is the starting point, right? We have increasing pressures on chemicals of concern, right? Yes, right, PFAS restriction. But if we don't have a growing supply of safe and sustainable chemicals, and that those chemicals are substituted, we're not going to make the kind of progress that we need to make. So let me take a step back, because we talked a little bit about defining substitution or defining alternatives assessment yesterday. This is actually one of the best reports that the Commission has funded back from 2003, a report that defined substitution as replacement or reduction of hazardous substances by less hazardous or non-hazardous substances, or by achieving equivalent functionality. So this functional approach already was in the substitution literature back in 2003. And they talked about a hazard reduction approach, not a risk reduction approach, but a hazard reduction approach. Because if you reduce the intrinsic hazards, exposure becomes less relevant, less important. So we reduce risk by reducing hazard. This is the EPA definition, which I like, of informed substitution, which is, you basically have a considered transition, a thoughtful transition from a chemical of concern to alternatives that are of less concern, using the best available information to avoid unintended consequences. Because we know we're never going to have perfect information, we use the best available information we have to drive change. So we do have, like, for risk assessment, there's the National Academy of Sciences Red Book on Risk Assessment. 2014, we created the Green Book on Alternatives Assessment to say, this is a science. This is a science policy approach. And we defined it as a process for identifying, comparing, and selecting safer alternatives to chemicals of concern, basis of their hazards, comparative exposure, performance, and economic viability. So this isn't a risk assessment. This is really about, you've made a decision to do something, weighing the pros and cons of options, and making a choice. It isn't about finding a safe level of exposure or understanding everything about the life cycle. It's about choosing a better alternative. And there's a series of steps in the literature. I won't go into them, but importantly, sometimes we don't have better alternatives and we have to design them. And it's okay to admit that we don't have better alternatives, and then we need to put the attention into the system to develop those alternatives. So we developed a set of criteria for alternatives assessment. This was a multi-stakeholder group of NGOs, government, industry, academics to say, okay, what are our goals here in alternatives assessment? Well, it's to reduce hazards. We want to minimize exposures. We want to use the best available information, not get caught up in paralysis by analysis. We want to make sure that there's good information to make informed choices. We want to understand that there are always going to be trade-offs and make those transparent and try to resolve them to the extent we can. And ultimately, it's about taking action. And for me, that's the most important part of alternatives assessment. So my mentor, Mary O'Brien, wrote probably the best book on alternatives assessment called Making Better Environmental Decisions and Alternative Risk Assessment. And what she said was, this is empowering, right? One of the most powerful and essential steps to understanding to change is understanding there's alternatives. It gives you hope, right? I teach students about environmental health. By the end of a semester, once they hear all the problems, they're ready to jump off a bridge. So we need to have hope that there are solutions because we can drive those solutions. So what I teach my students is we're going to study the problems, but we're always going to focus on what are the solutions. How do we drive solutions to those problems? The National Academy of Sciences had a report back in 2012 that says the same thing. We spend too much time putting all of our scientific attention into figuring out how bad it is, but that doesn't solve problems. We need to figure out how to do better. So that's the basis of alternatives assessment. As we talked about, right, there's these essential parts to an alternatives assessment, which is a decision to substitute, right? We start with the function, as Romain spoke about yesterday. We need clear and consistent processes. We don't have to repeat the same. We need to adapt those processes to different contexts, but we need to have consistent definitions of what's better. And we'll talk about that in a little bit. And then just to avoid paralysis by analysis, if you look at the safe and sustainable by design criteria, you'd need 3 PhDs to do the safe and sustainable by design effort. That will never work in industry, right? So we need to be ahead of the science, right? The decisions to substitute are happening in industry. You need methods and approaches that allow them to weigh those alternatives, evaluate them, be thoughtful about them, but understand we're not ever going to have perfect information. So letting perfect be the enemy of the better is just you're going to end up with regrettable substitutions. So again, we talked about this idea of functional substitution, that the alternatives don't only have to be chemical alternatives. They could be product change alternatives, or they could be solutions at a service level. So you take BPA and thermal register tapes, right? You can replace it with another bisphenol compound. You can come up with another printing method, or you can just replace the function that you have, which is documentation of a transaction, and use an electronic receipt. So there's different ways to think about this at a product level or a process level. So let me give you an example of how we've thought about this, right? So trichloroethylene, the US EPA just put out a significant risk notification of trichloroethylene. We've known trichloroethylene as a carcinogen for 40 years. Now it's a significant risk. So back in Massachusetts, starting in 1999, we started working with metal finishers and others in Massachusetts, understanding that trichloroethylene was one of the most common chemicals we'd find at hazardous waste sites. Companies didn't really want to use it. It just works really well in metal degreasing. So we started working with those companies to identify alternatives, both aqueous cleaning options as well as ultrasonic cleaning options. We removed the technical risk for those companies by evaluating the alternatives in their own manufacturing processes, and then supported them to adopt the alternatives. And we reduced TCE use by 95%. Never did a risk assessment. We knew it was bad. We didn't need to do a risk assessment because we knew it was bad. We needed to drive solutions. So we did. But you take here in Europe with the authorization for TCE, and Daniel Slunga here in Gothenburg did an analysis of what companies switched to in metal plating when they were told they couldn't use TCE. They used perchloroethylene, which is a regrettable substitute. So they weren't focused on what the alternatives were, right? They were focused on getting rid of the bad, not transitioning to the better. So, this is where, if we think about where we need help in alternatives assessment from all of you, is really, we know we have data gaps. We know newer chemistries often have much less data. So how do we get those data quickly so we understand, we create the red flags? So new approach methodologies are one way, modeling is another way. So we need the science to be able to accelerate our ability to evaluate alternatives effectively and not get caught up in paralysis by analysis. So hazard assessment is one area. Understanding how to think about PMTs in alternatives processes is really important. Thinking about ecological endpoints more effectively. Thinking about what the exposure trade-offs might be, the intrinsic exposure trade-offs between options, because the form of that chemical is different or the volumes used are different. Thinking about how we make a decision. So Roman was talking about that yesterday. How do we put all this information together and make a decision effectively, understanding what our trade-offs are? And then life cycle, right? How do we think about these life cycle elements? Because increasingly companies are being pushed to consider scope 3 emissions, biodiversity. How do you bring those elements without getting caught up in paralysis by analysis? And then ultimately, how do we use our science of hazards, of problems, and apply that to designing new chemistry? And there's a whole area of chemistry called rational design. So how do you take the knowledge about hazard and then design those hazards out of the molecules in the first place? And there's a very good example, actually. The Valpures in marketplace, right, Anna? Yes, thank you. So thank you. I had to, sorry to put you on the spot. But a very good example is how Valspar, now Sherwin-Williams, went to look at alternatives to BPA and canlines. So what did they do? They took a rational design approach. They identified what part of the bisphenol molecule leads to endocrine activity. They then designed out that part of the molecule that leads to endocrine activity, and being very smart about it because they knew another bisphenol was being critiqued because it's in that class of bisphenols. Two of the scientists there had been at EPA. They knew how to think about stakeholder engagement. What did they do? They gave their science, they opened their science, they had the most critical scientist on BPA, Estradinas de Anosoto at Tufts University, evaluate their science and poke holes in it and said, tell us it's not endocrine active. And what she did was say, it's not endocrine active. So that idea of thinking about how to open up the science to be critiqued, particularly when it's in the same class of chemical, is really important. But it shows that you can use science of problems to design better solutions. But we know that identifying alternatives isn't enough. They have to get into the marketplace, right? They have to get to scale. So we have to think about those barriers to substitution where we can identify unexpected trade-offs, and then we need to support companies in making those decisions. And where there are suboptimal alternatives out there, we've got to design better ones. So we know there's a lot of barriers to substitution. They all relate to the incumbency of the existing chemistry. It's been optimized for 30 years. It's integrated into complex supply chains, as Maria was noting yesterday. It costs less. There's a whole set of costs to transmission chemistry, reformulated chemistry, and the alternatives don't have that benefit. So we need to figure out how do we incentivize and grow those alternatives. And there are those drivers, regulation, consumer awareness. So we need to drive those accelerators more effectively. So as I said, those costs or those barriers are real. They relate to the costs of R&D, new capital, reformulation, retraining. Those costs are real. Performance, it may not perform the same, or you need to use, it's a multifunctional, and now you've got to come up with 3 solutions to replace that multifunctional function in a product, or you need to think about those changes of product design to meet performance needs. Supply chain, right? No company wants to go with a single supplier of an option, so you need multiple suppliers of an option. You have to deal with the complexity of a supply chain 3 tiers down. Can you get that basic chemical that leads to your more refined chemical? Then there's the regulatory side. Often new chemicals that are greener are at a disadvantage because they have to go through the same regulatory hurdles. The incumbents have already gone through those hurdles. They're on the market already. So how do we expedite the entrance into, for safe and sustainable chemicals? And those timeframes for R&D in the regulatory side, I was thinking the revision, how many years was the option 1 in the PFAS regulation was like 3 years, 2 years? How many years was it?
18 months.
18 months. So 18 months to drive solutions. R&D timeframes in the chemical industry from a new chemical design through to scale could be as long as 14 years. So 18 months, 14 years. If you have 18 months to substitute and it's something that needs to be reformulated, rethought of, you're going to end up likely with a suboptimal solution unless it's already there. So, and then there's the lack of clarity of what are we moving towards. So we know that there are these challenges, but we know that there are solutions. We've learned a lot about how do you bring together supply chains to solve problems. Companies are willing to work together to solve problems, to identify barriers, to overcome those barriers, and they can work together. And we can drive, we can define what's safer. Ramon showed the OECD criteria yesterday for safer chemicals. So there are some interesting criteria that, have the minimum. What's the minimum we want to know to ensure something's a safer alternative? And ideally, what would we want to know? And we can apply that differently in different contexts. So when we were looking at AFFF alternatives, we had a set of criteria. There were certain chemistries we knew we just wanted to avoid, some of the cyclic siloxanes. And then there's a minimum set of criteria for defining safer, but ideally, right, we would want to know about mobility. So there's a whole set of additional hazards ideally we'd want to know, but at a minimum, we want to know that. So we can think about minimum versus ideal, right? Minimum to understand that it's safer. Ideally, to really have a better understanding that it's safer, we'd want to know more. But we can't know everything. The safe and sustainable by design criteria add in additional complexity about sustainability. We won't get into it. The commission has a meeting the next 2 days on this question. All I can say from looking at this is if it's not simpler, it's not going to be usable. It's an academic exercise right now, which is great for academics. We love to sort of cogitate and think about things a lot, but in industry, it's not very useful. So we also need to rethink performance, right? We heard about this yesterday, that the way we define performance is often a single performance metric for everything, right? AFFF works great in everything, right? Some fires, what we found from the testing is for most fires, you don't need AFFF. For a small percentage of fires, AFFF works a lot better than other options. But as we start parsing that around, if we only have a single performance metric, we'll never lead to alternatives. So we need to think about what we call sufficient or fit for purpose performance assessment to think about the range, right? Like, is it best, is it sufficient, or is it inadequate? But also to separate out that performance of, does it do what it needs to do versus is it feasible? Feasibility relates to, can I use it in the same equipment I have today? So AFFF alternatives, there are very good AFFF alternatives that put out fires just as good as AFFF. You just can't drop them into the same equipment you have today. Well, that's a different story than do they work? So you got to think about that, and then think about what are our trade-offs? Why isn't health, safety, and environment put on par as a performance criteria with cost and performance? So how do we bring other performance criteria, health, safety, environment, as an equal performance criteria? So, how much time do I have?
We only have a leaf thought.
Oh, good. Okay. So as we think about policy, the same thing, right? You need policy. If you look at innovation theory, you need policy that is push policy, right? Willingness. Willingness is often created by market demands, investors, or regulation. But you need capacity and you need opportunity. That's the pull policy, right? That's the incentives type policy. So what we've learned from policy over the years is you definitely need regulation. You need clear criteria for where you're going. But you also need these pull policies, right? You need support. You need technical assistance, demonstration, supply chain engagement. You need incentives, recognition for better. You need, alternatives assessment. You need networking and collaboration for driving solutions. So all of those are key. And the report we did for the commission that actually was cited as the basis for the safe and sustainable by design is really laying out those types of steps, right? You need to improve information. You need to enhance supply chain engagement, and you need a better policy mix that both pushes and pulls in the system. So let me wrap up by talking about an example. This is one we've worked on. This is a PMT, so there's a chemical in tires called 6-PPD. It is an anti-ozonant. It keeps tires from breaking apart, so a tire would probably fall apart in 1,000 to 5,000 kilometers if it didn't have this chemical in it. But 2017, you see these studies basically saying that a degradation product, an ozonation product of 6-PPD, creates a quinone, 6-PPD quinone, which is highly toxic to coho salmon and other trout. Actually, if you look at it compared to the toxicity of other aquatic toxicants, it's the second most aquatically toxic substance we know so far. So we're talking something that's really, really dangerous. So what do we do about it? We put together a meeting in December with tire companies, chemical companies, authorities and scientists, and then tribal and environmental leaders. The chemical industry isn't even debating whether this chemical is bad. Dead fish help, to elevate the problem, right? If this was some obscure human health effect or effect, you wouldn't see the same action. So what can we do about it, right? We can change the bioavailability. We can try and keep the 6-PPD in the tire so it doesn't hit ozone and then create the quinone. We can change the molecule. We can change the rubber material, or we can change tire design. One of the challenges is the anti-degradant has multiple functions in a tire. It's an anti-ozonant, it's an antioxidant, it protects the tire under stress, and it ultimately keeps the tire safe. And then you've got the complexities of a tire, right? A tire is multiple layers, right? You have the outer layer, which changes about every 5 years. The inner layer of the tire, typically the time frames for that to change are 30 years. Typical inner core of a tire hasn't changed in 30 years. But the PPD migrates between the whole tire. That's how it works. It's basically a liquid mixture and it moves around in that tire. So it goes out to the sidewalls. That's how it keeps the tire rubber soft. As it migrates out, it comes to the surface and gets out. So it's designed to come out of the tire. So you have this problem here, right? It's not easy, right? There's not a drop-in substitute's going to have to do all of these things. And thinking about, and it has to be safe, right? Tire industry is not going to compromise on safety. So you got this giant problem. And then you add in one more problem here, which is the tire industry is changing its formulation. So if I'm a chemical company and I'm designing an alternative, and that alternative is not even going to be on the market because tires are going to be totally different in 10 years, why would I spend millions of dollars? So there's a whole set of problems. Essential chemical, but really dangerous and problematic impacts. The performance has to work. Government sets the standards on performance, which probably are overprescribed because there was an incident involving tires, which led to litigation. So can we adopt those changes? So 6-PPD is the only thing that can meet the performance standard right now. The timeframes are long. The chemical companies are saying, well, we can design the alternative, but what do you want us designed towards? What are the criteria for safer that you want us to have? What tests do we need to do? What do we need to have? So, and then, multiple suppliers. So no one supplier can make enough of this chemical for the whole tire industry. So you're going to need collaboration among suppliers. So what we're looking at now is, are there rational design alternatives? Given the need, right, even a drop-in will be a 6 to 8 year process for tire design to change. Probably in that outer core of the tire only is the only place we'll be able to make change. If you wanted a radically different chemistry, you're talking probably 10 to 20 years to change the tire. And in that period, tires are likely going to change anyways. So this is the complexity, right? This is a really complex case. But it tells you why we need to be really thoughtful about this, because the alternatives that are being thought about right now, the other PPDs, also create the quinones, which are highly toxic to fish. So if we jump to a drop-in, we're going to end up with the same problem again or a different problem. So ultimately, to wrap up, this is driving safer alternatives is tough, right? We need to change the policies. We need to push policies. We need to pull policies. We need to expand our science, not just the science of problems, but we need to marry that science of problems with science of solutions, and bring those together more effectively. And we need to transform the markets, which Anna spoke about in her panel. We need also to the demand side, but we also need the supply side support to drive those alternatives at scale. And then ultimately, we need a bigger community of solutions, problem people and solution people to come together. So this is my plug for the A4. I've got some flyers there for everyone, but it's not easy, but I'm hopeful. I have to be hopeful because otherwise I wouldn't be here today, that we can actually do this if we but we have to think differently about our problems and our solutions. So thank you. I'll stop there.
0 p.m. Zero pollution of persistent and mobile substances. This project has received funding from the European Union's Horizon 2020 Research and Innovation Programme under grant agreement number 101036756.